So welcome, everyone. It's my pleasure to introduce Rebecca Stewart from Duke University, where she's an assistant professor in the statistics department, and she's also affiliated with the computer science department. Rebecca has received the MIT's TR under 35 recognition, and interestingly, she's also working with the US Census Bureau, helping them with important issues like the record linkage and entity resolution for the census data. So without further ado, let me invite Rebecca to give her talk. Thank you.
Thanks so much, Vivek, and thank you so much for having me. I'm going to talk about a lot of large-scale new Bayesian entity resolution work that my group has been working on. And this has largely been done by a PhD student that I'm co-advising at the University of Melbourne in the CS department, Neil Marchant. And he's co-advised by Ben Rubenstein. So I just want to start out by explaining what is entity resolution and other names that it is associated with in the field, because typically I work at the intersection of statistics, computer science, and machine learning. So our goal is to identify records across and within data sources that are quite noisy and they refer to the same entities. So in terms of entity resolution, this is also known as record linkage, data matching, de-duplication, data integration, and many others. So I think also in this group it's known as data cleansing. I'm sure there's other different types of terminology that you could refer to entity resolution as. The way that I think about this problem is you have multiple noisy databases, so they could be industry databases, and you could have more than 3 of them. So you could be linking to arbitrarily a large number of databases that I have up here. And the goal is that I'm thinking about that I have duplication within a database and across them. Now, what I'm thinking about here is maybe I'm trying to understand if this Steve Feinberg here is the same as the Steve Feinberg here. And if they're the same, I'm going to put an edge saying that they're co-referent. Now, if the Steve Feinberg over here is not the same Steve Feinberg as the one here, then I'm going to drop the edge and say that they're not co-referent. Now, what I'm thinking about here is I'm defining an entity, which could be a person or an object or just about anything. I'm thinking about this, just putting it on a node as a graph here, and I'm just representing the name or something about the entity. But I, of course, have other information typically about the entities. And if I don't, it's going to be very difficult to actually say that they're co-referent or non-co-referent. So again, I have some sort of information about the entity. So maybe, I have my former colleague, Larry Wasserman from Carnegie Mellon, but then I have other information that I can scrape from the web. So maybe I have information about where Larry lives. There's some sort of phone number, and I have other information that I know about him that is in these databases that we're collecting all the time. Oftentimes, I don't actually have a unique identifier. So as people are moving and merging and more in data is collected, and especially as we have more and more databases, we may not have a common unique ID. So for example, if I'm looking at 2 different Steve Feinbergs, so this is often how training data is actually gathered, I may be looking at these 2 Steve Feinbergs. So, it's, I think, quite easy to see using subjective knowledge that if I believe the age ranges are quite accurate, that these are not the same Steve Feinberg. Although if I end up looking at a map, these 2 addresses are quite close to each other. And one of these addresses, neither address is actually at Carnegie Mellon. So if I think about this problem, I want to the goal that I'm thinking about is I want to be able to do the entity resolution problem in a model-based fashion that's automated. I want to do it in an unsupervised way because I may not have training data, but if I have training data available, I certainly want to be able to leverage that. And I, most importantly, would like to know the uncertainty of my entity resolution task, and I'd like it to be generalizable to many, many, many different applications. And feel free to jump in if you have questions.
When you say training data, are you referring to labeled data with like certain pairs?
So in the examples I'll show to illustrate the methodology, I will have labels, and at the end I'll show where it's very difficult to do any type of crowdsourcing or labeling at all. And so I'll show some work that we're doing further on that, and feel free to jump in regarding that. Yeah, so we handle different types, and this is why we're motivating this in an unsupervised fashion. So just to give you an example of what might motivate this, so something for example, if NGOs are collecting data in the Syrian conflict, or if I'm looking at census data. So if I'm merging together census data, or if I'm merging together data sets where individuals have been killed in the Syrian conflict or in a conflict war, typically I have information that has the same type of structure as the westernized example. However, I have different types of a name. So here I have Syrian Arabic. If I'm looking at the El Salvadorian conflict that I'll turn to later, I'll have Hispanic names. If I'm looking at the US Census data, I have all kinds of different names. So then I have to think about what types of distance functions I'm going to use for all of these different types of names. And most importantly, I don't always have the sense of a unique identifier. So not everyone actually will have a social security number. And especially here, I actually don't have a unique identifier. And if I actually go and try and match these or try and do some sort of crowdsourcing, this can actually be incredibly difficult. And I'll return to this at the end after I go through the methodology. Really good question. So I want to talk about why entity resolution is difficult. So let's suppose that we have a total of n records and a total of k databases. So we'd like to seek models that are much less than big O n to the k. So for a lot of us, this might just be quadratic, but what I'm considering is that I want to look at the entire space because I want to propagate the uncertainty to some type of downstream task. So that might be some type of prediction task like linear regression or logistic regression or any prediction task. And I also want models that are reliable, they're robust, they're generalizable, all of those types of properties that we want. And if I think about just 1 and 2, these fundamentally go against each other. So if you just look at the literature, there are very, very, very few properties that satisfy both 1 and 2. So then finally, if I go to 3, so this is a very bit of a subtle issue, but we would like models and algorithms that are going to handle what I'm going to call unbalanced data. So unbalanced data, if I think about the entity resolution problem, I have duplicate entities in my data, but they take up a very small fraction or percentage of the data. And so this is what I mean by unbalanced. So typically, if you look empirically at the types of applications, roughly maybe 1% to 30% of the entire data is going to be duplicates. And if you think about the data sets where it's between maybe 1% to 10% are only duplicates, this incurs mixing issues, and it's very, very, very difficult then to find the duplications. And so this is what I mean by duplicates, but I mean by unbalanced data. So I just want to talk a little just quickly about established entity resolution methods. So these are just a few in statistics. There are many others in the database and computer science community. The most fundamental one that was first introduced in the statistics community is the Fulligan-Center method. So this is based on a likelihood ratio test where I look at the likelihood ratio of one record compared to the likelihood ratio of another record. And if it's larger than a threshold, then I say that it's a match. So this is a bit problematic because it's saying, okay, well, to pick that threshold, I have to have a large amount of training data that I really believe on. And then this has actually encouraged a lot of development on semi-supervised methods in the machine learning, computer science, and database communities. And it has the same fundamental problem. So the same fundamental problem with random forests, support vector machines, deep learning models is if you don't have reliable training data, your models are going to be wrong. You're not going to know how to tune them. And then there's also going to be another fundamental problem. So the other fundamental problem is if I think about, so suppose I have a record A that matches to B and B matches to C. I want to be able to say that A is then a match to C. So I want to have what's called a transitive closure in mathematics. And all of these types of probabilistic semi-supervised methods, they don't easily satisfy transitive closures. So the easiest way to understand this is to think about a hypothesis test. So if I think about imposing a transitive closure under a hypothesis test, there are many ways to actually write out that transitive closure. So if I want to do that, for example, for the Fulligan-Center method, if I'm looking at k databases, I have to look at all the different k tuples, all possible values, And that actually is going to blow up computationally. So that's very problematic. So this is why transitivity is typically never included in anything like a semi-supervised method or in the Fulligian center methodology. So there's also a ton of work that's been done in deterministic linking. Of course, this is very problematic in terms of figuring out, well, when am I actually making a mistake? Another big issue is there's a lack of uncertainty quantification. There's also awkward post-processing. So in addition to issues with a transitive closure, you don't know the actual uncertainty that you're then passing to your prediction task. So you can put a bound on it, but you can't say, okay, this is the amount of uncertainty that I'm taking from the entity resolution task, and it could be quite large. So if the training data is quite, has a lot of noise in it, then intrinsically you'll be passing a large amount of error into your linear regression. And then your linear regression will be quite off. But then you're not taking any of that into account and you're ignoring it. So this is why I'm advocating for a fully unsupervised method. And so what I'm going to do is kind of lay out the basic idea, some basic ideas that have appeared in Bayesian methods, both in the machine learning, computer science, and also statistics communities, and show you some developments that we've done in my research group that have been led by a PhD student that I'm co-advising, where we've actually scaled these into the millions in a distributed setting. So what we're looking at here is, in the Bayesian setting, we're building off of a couple of different types of frameworks in some work that I did as a postdoc at Carnegie Mellon with C. Feinberg and Rob Hall in 2014 and 2016. So this work appeared in AI Stats. And the basic approach here is we don't want to compare other records to other records. Instead, what we want to do is we want to look at a bipartite graph. So why a bipartite graph? The idea is I want to be able to cluster records to a latent entity. So this latent entity is the true value of, for example, UVivic. And I don't know this, but if I had an oracle, I would know this. So instead, since I don't know the oracle, I'm gonna draw this from some distribution. And this distribution can be quite flexible, and it's going to be application specific. But you can draw, I'll show different types of models that will work for this. But the key approach is I'm never going to link records to records, and so I'm going to get a computational savings here. So the idea is to eliminate low probability matches. So what this looks like in terms of in a general framework is I have an arbitrary number of databases, then I have records within those databases, and then I have features, a common number of features here. So I'm going to take that record and I'm going to cluster it to a latent entity. So this record, it could be categorical, it could be string valued, it can be a very general distribution. So if this is categorical, it would be categorical theta L. For example, if the data is anonymized and it's health data. Now, it could be a much more complicated likelihood function if it has string data and textual data in it. So that likelihood can change. And also the distribution on the latent entity can change. Now, lambda is simply saying, okay, this record points to these latent entities. So it's giving you basically a pointer function in terms of the database structure. So it's telling you the edge structure, and it's going to update at every Gibbs iteration. Now, the other key kind of construct here is, well, we believe that there's noise and distortions in the data. And so we want to measure that. So we're going to build a measurement error model. And this is based on the hit and miss model, or you can also think of it as a spike in a slab model. So what I'm saying here is, okay, I'm going to call this a parameter Z. And so Z is going to be the amount of distortion I believe is in the model. So the easiest thing I can do is put a Bernoulli coin flip on this, and then I can tune that with a parameter beta L. So I'm doing this at the feature or the field level, where I'm thinking of the feature as being maybe first name, last name, date of birth, things of that nature. So I'm looking at every particular field or feature. And then I can continue putting out more flexible distributions on each of the parameters. So what does this look like graphically? So instead of, again, looking at record pair comparisons, again, I'm going to cluster these records to this latent. So the records are the nodes. This is the latent. So I'm taking all the Steve Feinbergs to the latent S. And then these edges here are representing the linkage structure. So they're representing the connections. So they're the edges. So everyone who points to the latent entity, if I'm looking this in a database or graphical structure, they would have the same value or number. So maybe it would be 8, but the label doesn't matter. Now I want to differentiate between the Ryan and the Rob Tibshiranis. So I want to cluster all the Ryans to a latent R. And so I'm just noting the difference, so if they have a different value by now coloring it in red. Yeah?
Do you need to specify like how many is the latent variables?
I'm going to put a prior distribution on lambda. So all of these are going to have some distribution. So for example, lambda is going to I'm going to show the model in a moment. The lambda is going to end up having a discrete uniform prior, but you can end up putting a more subjective prior on this, and I'll show that at the end. So I'll show the model in a moment. I just want to show it graphically so you get an idea of intuitively what I'm doing before I give the model. But I'll give the full model.
Could you go back to the example?
This one?
Right.
Yeah.
So how did you know that the 3 Steve Feinbergs all should point to the same latent entity?
So this is what, so I'm saying this is what I would want my model to do. And what I'm going to show in a moment is how you build this model. And then I'll show you some results for this model.
Simple clarification.
Yeah, sure.
So is this the bipartite graph you were talking about?
Yeah, exactly. So if you notice, right, it's now bipartite, and it's bipartite at every Gibbs iteration. And then with a tiny bit of theory, you can actually show that you can make it bipartite for all Gibbs iterations. And so that is, I proved that in Stortz Hall Feinberg 2016. So here you get that's a very good question. So there you get the bipartite structure. And so you still get that, you get a K transitive closure if you just extend these out to K. So that's actually what I showed. Okay, so I'm going to show that we can actually scale Bayesian entity resolution methods to actually millions of records without sacrificing accuracy and crucially giving uncertainty of the entity resolution task. So what I did in the previous papers is I built a methodology for categorical and textual data and showed lots of sensitivity analyses and applied it to many different data sets. And so what I'm doing in this work that my PhD student Neil is leading is he's actually taking the model and he's putting it in a distributed setting. So what I'm going to do first is I'm going to lay out the large ideas that we're doing here, and then I'll lay out the model if you'll just be patient so you can see all the details.
So can I ask the clarity?
Yeah, of course.
So when you say without sacrificing accuracy,
so I'm going to
understand, well, because in my head, kind of the only way to know if you're accurate or not is to have a oracle tell you. Like
so we compared to 5 different data sets at the end where we actually know the ground truth. And then what we're doing in new work is we're comparing it to where we don't know any oracle information at all. So when I mean we're not sacrificing accuracy, so what I'll end up showing, or I'll end up just stating because the proof is quite long, is that the distributed version of this model, the marginal posterior is the same as the original model that I had for the model that I'm going to show you from Stortz 2015. So I'm going to lay out that model, and then I'm going to show the extended model.
So you're basically comparing to the non-distributed setting, the results.
Where we compare to it when we can, because it's not very scalable.
Okay.
Yeah, because it's just using a Gibbs sampler. You could scale it to a certain point, but doing comparisons with that, you would have to run it for a huge amount of time. Yeah. So when I say accuracy here, I mean things like the posterior distribution, the precision, the recall, things like that. So we actually don't give up anything. Okay, so the main objective and the main things we're doing in this paper is we're incorporating auxiliary partitions. So the auxiliary partitions This is similar to what's known as blocking and entity resolution, where in the blocks you actually partition, typically it's the records. You partition the records such that you can do some type of dimension reduction, such that you only then you only do the entity resolution task within the partitions. Now we're doing something very differently here, so we can actually do distributed computing. So instead of actually building partitions with the actual data points, we're actually partitioning up the latent entities. So it's quite different than blocking. So we're not actually calling this blocking. We're going to call this partitioning, and this is coming from the database community. So these auxiliary partitions are actually going to induce a conditional independency between the actual entities. And this is very important because this will actually enable us to do distributed inference at the actual partition level. And importantly, then you can actually show that the marginal posterior distribution is actually preserved of the original model. So the partition function, which is going to actually partition up the latent entity, so these are the Ys that I showed before, is going to group similar entities together. And it's at the same time going to preserve well-balanced partitions. So the type of partitioning that we used in the paper is called KD trees. You could certainly try other things, but we just wanted to experiment with one particular type of partitioning. And something we're looking at now is other types of partitionings and looking at unbalanced partitions. So the other thing that we looked at here is we employ a partially collapsed Gibbs sampler in the context of distributed computing. And we actually looked at a couple different ones, and this ended up being a tricky point in terms of implementation. So then we're using some standard computational efficiency tricks. So there's a subquadratic algorithm for updating the links that's based on indexing. For the attribute similarities that I'm going to look at, so if I'm comparing, for example, my name to Vivek's name, it's not going to be very similar. So I'm going to truncate that down to 0, and I'm never going to compare it because it's not very sensible, and it's actually quite wasteful. Then the final thing we're going to do is based on the likelihood function, you can actually write this out in terms of a nice perturbation type of likelihood where we can actually then do a faster speed up using what's known as the Vos-Alias method, which is also coming from kind of a low-hanging fruit from the computer science community. Okay, so first I just want to give the assumptions, and then I'll explain what the model looks like. So we're assuming that we have multiple tables or data sources. We have duplication within and across the tables. The attributes are aligned. The attributes are discrete. We can also have textual data. We have missing values, and we're assuming there's no ground truth, so it's unsupervised. If we do have some sort of ground truth, of course, we can use this in order to look at some accuracy metrics, but it's not actually embedded in the model at all. So the output is going to be some approximate posterior distribution that's going to be over this linkage structure. So we're getting links and non-links, basically. So we're getting, if I go back to that picture, I'm getting that entire estimated edge set. And then I can get summary statistics of those. So I can actually get a full distribution. I can look at credible intervals. And I can look at functions of the actual linkage structure. Okay, so finally the model. So first I'm going to explain the original model, which is from a paper that I wrote in 2015. So it's known as Blink. So there's a R package for this on CRAN. And so the idea is you have a fixed number of population entities, eta here, going from 1 to e. Now, you have an entity attribute that has a finite domain with some distribution phi sub a. And then the way that I'm going to generate a latent entity is I'm going to take e for the so I'm going to take the latent entity, which depends on the entity value and the attribute level, and I'm going to draw this from the empirical distribution of phi sub a. So why am I doing a draw like this? Well, it's very cheap to do, and it's basically doing an empirical type Bayes approach. You could certainly do something different, and I'll lay out something different at the end of how you can do something in terms of a Bayesian non-parametric approach. But this is a quite cheap approach and a quite kind of data-driven approach way to do this. Now, the linkage structure, the way that we're doing this here, you have some sort of record that's in the table, and it's going to be linked to an entity, which we'll denote by the linkage structure for the table and the record. And we're going to say it's linked uniformly at random. So the linkage structure for a table and a record is going to be drawn by a discrete uniform distribution over eta here. So if I think about this is just a discrete uniform from 1 to the maximum number of records. So why did we do this? Well, it's quite simple, and it was an easy way of understanding if this type of methodology works in practice. Now, what we've shown in other papers, such as in a NIPS paper, is that you can actually look at a full non-parametric class of priors on here, and they're quite flexible. But the thing you have to give up is the distributed part. So that actually breaks down. So that's something that we're working on now. Okay, so here's the distortion part. So the distortion, so I'll go through the distortion and then the likelihood function. So a distortion probability is going to be associated with each attribute A and a table. So I'm going to draw this from basically a beta distribution here, where these crucially can depend on the attribute level, because they should be different for each attribute. And then here, this is going to be the distortion is going to come from a Bernoulli. So this is going to be semi-conjugate here. Now, the likelihood function is going to come from this hit and miss model. So if the data point is the same as the latent value, then it's not going to be distorted. So the data point and the latent value are going to be the same. Now, if it is distorted, I'm simply going to draw from this phi distribution, which is coming from, so I'm going to draw the empirical distribution function, and then I'm going to look at a normalized version of the difference at each attribute level of the latent value and the observed value. So the whole idea is I'm taking Vivek's record, so one of his features at the attribute level, such as his name, and I'm comparing it to the latent variable. And so this is why for the distributed version, you have to partition the latent entities, because this is a latent entity type mixture model. Okay, so in the new approach, so we're proposing a distributed version of the original model, and it's much more general and it's much faster. So the previous version only scaled to about 500 or maybe 800 records, and this would take probably about a week to run because it was very slow for mixing. Yeah, go ahead.
You said distortion in the previous.
Yeah, sure.
How does that connect to things like distance functions?
So the distance function, so here you can write this, you can write the similarity here as 1 minus the distance function.
But you're assuming that you know the distance function?
So yeah, so I'm assuming that the similarity function or the distance function is known, and this will work for any distance or similarity function that's bounded. So, for example, if I'm working with some type of English name, I'd probably recommend using something like Jaro Winkler. Now, if I'm working with a Hispanic name, I'd recommend working with the Monge-Elkin metric, which is a little bit, I think, less familiar. Or you can actually, something we've been doing and Neil has been doing is modifying this to make it a more asymmetric function. So you can also modify this definition to work with asymmetric distance functions. But if you think about this, this is going to be very application specific regarding which similarity or distance function you should use.
But there's also a question of, is the similarity function at an attribute level or is that a record level?
It's at the attribute level.
Okay, but what if I also want to look at it as a whole record? So let's say I want to sort of tokenize, have a notion of like set similarity. Can I express that in this framework?
Yes. So if it's okay, just because it'll take a while to talk about that, I can talk to you about it offline, but yes, you can do that. You can do that quite easily. So you could just reformulate that, what you've just said, as being a different type of attribute. It would just be a different type of reformulation. Yeah. So I'm assuming you'd want to do some sort of tokenization or hashing and then do the, yeah, that would work fine. That's not a problem. So there's a lot of differences in this model versus the previous model. So the modeling differences, for example, are supporting missing record values. So far we're just doing missing completely at random. Something we'd like to do in the future is missing not completely at random, but that's much, much, much harder. We'd like to support, so we're supporting arbitrary attribute similarity functions, so one for each attribute. So we found that this is quite important to do. Also, we're incorporating this different type of auxiliary partitioning of the latent entities. So again, we're partitioning the latent entities and not the records. And this is really, really, really crucial to doing, to being able to break up the model such that we can actually apply a partially collapsed Gibbs sampler. Okay, so the auxiliary partitions then enable us to actually do distributed inference. So what you can do is you can actually prove that the marginal posterior is actually unchanged. So this is very, very, very nice. The partition space of the entities basically looks like the following. And we have to use a deterministic function at the moment. So we have to take this space here and map it onto a space of partitions 1 to p. So this is why, for example, we're using KD trees. So the set that we map onto needs to be completely deterministic. So then what we do is we update the model. So record R and table T is going to be assigned to some partition, which depends on the table you're in and the record value. And then we go to an entity of lambda TR within the partition. So the way that this works is we look at the conditional distribution of the partition given the latent. So this is going to be some discrete function of this. And then for this next step here, we look at the linkage structure given the partition, which is then going to be discrete uniform in terms of eta given the partitioning structure. So why this? Well, it's going to take the partition space of entities and go to the actual realized space of entities. And then as I'll show in a minute, as we're going and basically going through one iteration of the partially collapsed Gibbs sampler, we're going to allow at some place actually the partitions to swap. So if you actually have gotten an entity wrong, it can actually move across the partition. And this is quite nice because you can actually then resolve mistakes. Whereas in pipeline approaches, you can't do this. Okay, so again, we're doing approximate inference here. So what we're proposing to do is a partially collapsed Gibbs framework. So we're having to do regular Gibbs updates for the distortion probabilities and the distortion indicators, and also the links. Then we're having to do, if you're familiar with PCG, we're having to do marginalization and trimming. So this is going to be applied jointly to update the entity attributes and the partition assignments for the linked records. And the actual order of these is really, really, really important, or otherwise the stationary distribution is not actually preserved. So one thing I'd just like to point out is the vanilla PCG framework of Van Dyke and Park from 2008 actually is very, very, very inefficient here. And so we had to do a little bit of playing around in order to find something that was quite efficient. Okay, so what does this look like at a high level? So we have some parameter theta. So again, remember theta is the parameter of the data that we have. So maybe the data x is categorical theta. So we're going to take theta and update it onto the master and broadcast it now to the workers. And then now what we're going to do is make an update of the linkage structure onto the workers. So here you'll see that all of the records, they have to link, the linkage is restricted to be within a partition. So now what we're do is we're finally going to update the latent entity and the partition on the actual workers. And now we can actually do moves across the partitions. So here we can actually do some sort of update that is based on this step here. So this is allowing things to move across the partitions. And then finally, once the newly assigned partitions are given, these are these are updated, and we update now the distortion, and then we calculate any summary statistics to now the master worker, to the workers, and then broadcast to the master, and then we repeat this again. So I just want to talk about a couple of the tricks for speeding up the inference. So there's two main bottlenecks here. So there's the linkage structure update. So this is the order of this is going to be the number of records and the number of entities. And then there's another bottleneck, which is the entity attribute update. So most methods actually don't take the attributes into account. They kind of ignore these. And here the order of this is going to be the number of entities times the domain size. And both of these are actually quite big. And you actually have to do these sequentially. So these are the solutions I talked about earlier. So we do indexing. So we're going to maintain the indices from the entity attributes to the entities. And then from the latent entities, we go to the linked records. So what does this do? Well, this allows us to basically prune for candidate pairs of records. So this is just a kind of intuitive way of doing a speed up. Then again, I talked about before, we're going to threshold similarity scores. So, if I'm looking at my record and Vivit's record, it's not going to be very similar. So that's just going to be thresholded out, or the same between myself and Betty. Yeah.
So maybe Silu asked the same question earlier, but the number of entities is unknown at the start. I mean, the number of records is known.
The number of true entities is unknown. So this is what you're getting. This is what we end up getting from the estimated linkage structure.
But like, how do you know,
So-
how do you initialize sort of the number of entities? I mean, I can understand there's an iterative structure where you can refine it.
Is there a marker? Oh, yeah. So the way that this is initialized to start is a discrete uniform from 1. So suppose there is 1,000 records, but this can be any size. You just initialize every record to be being in any cluster. Now, if you have some sort of prior knowledge or you run some maybe semi-supervised algorithm, you could make this a different partition. So again, every record is just in one cluster. So this is a very, very, very naive initialization. And you can definitely improve this. Yeah. Now, of course, once you have the posterior distribution, and you have new data coming in, right? You already have your initialization. So that's your updated prior on the linkage structure. So you already have a really good starting point.
So in your work, did you use the
We actually use this. In the new work we're doing, we're using these very subjective Bayesian non-parametric priors. And those, I'll show you even with this. This actually, I can go to a plot of this initializes quite quickly. So if I look at, so here's the rate of convergence versus, for example, blink. And so we can look at it. This is on one of the data sets we looked at. So here is de-blinked, so the distributed version. So even with a uniform prior, it's converging almost immediately here. Whereas the original one, it's even after 11 hours, it's failed to converge. And then I can even break this up at each feature level. So I can see how long it's taking each feature to converge. So this is why we look at each attribute. And this is quite important.
So are you saying the initialization doesn't matter?
It depends. So in my opinion, it depends on the data set. So this is why it's even more important to look at each. So if you see over here, right, for like the naive type of even though they have the same marginal posterior distribution. So for blink, it matters because of the way it was coded up, right? Because it's just a naive Gibbs sampler. But for blink, it doesn't matter. For de-blink, it doesn't matter. And the reason is because we're using a partially collapsed Gibbs sampler. We're using all kinds of computational speed up. So I would claim for de-blink, it doesn't really matter. Now, it could matter for some applications we haven't looked at, but what we're seeing typically is it's getting up here quite quickly, like almost immediately.
What's the true distribution of the data? is it like very close? Is it very sparse so that it's very close to the initialization?
This data set is really sparse, so it only has 10% duplicates.
So that's why maybe this initialization is good enough, right?
No, this initialization for a sparse data set is really bad, right? So if you have 10% duplicates in the data set and you put every record in every cluster, then your mixing will be very, very, very poor for a Gibbs sampler. So unless you have a very, very, very good perturbation or speed up method for the Gibbs sampler, then your mixing, you should expect it to look like something like the red line.
But if I understand correctly, you're saying the duplicates are not that many in this data set.
But that's why the mixing is slow. If the duplicates were more, then it would be more of a balanced data set and you would be able to find them quite quickly. I'll talk to you about it offline.
Okay.
Yeah. Okay, so what we ended up doing is we implemented 5 different data sets of varying sizes. So we started off with kind of a benchmark data set that we know pretty well. It's incredibly unbalanced in the sense that it has only, as I said, only 10% duplicates. And we started small just for testing, also to make sure we have quality control, robustness, getting bugs out. And then we went all the way up to 600,000, and we've actually tested up to 1 million. So here I'm just giving, these are the total number of records because we have ground truth on some level using something like social security number or something like that. If there's a star, it's a synthetic data set, and otherwise it's a real data set. So we tested on synthetic and real. Now, these are the number of tables. And then if we look at the unique ID and just use the unique ID to remove the duplication, these are the number of unique entities. So for example, in this application for synthetic data set to the Australian Census Bureau, there's only 400,000 unique entities, whereas in the total data set, there's 600,000. So you'll see that some of them only have categorical information, some have categorical and string information. And for us, it's quite important that they work on both types. Okay, so I'm just going to show a couple of results here, but they're quite similar for all of them. So what we compared to is our methodology. We're looking here at the precision and the recall, and then the F1 score, which is basically like an average of the precision and the recall. And then we're comparing to the Follagy and Sunter, as well as we compared to other semi-supervised methods using the same type of a comparison method. And when we look at other semi-supervised methods, they're roughly about the same. And this shouldn't be surprising if you think about the approaches. So what we're looking at here, so we can see the precision and the recall, for most of the data sets here, they're somewhat balanced. So when you're looking at a particular type of ER method, you'd like the precision and recall to be balanced. But one thing that points out immediately, of course, is, okay, our methodology is completely unsupervised, so the comparison already is very unfair. And then you can see also this issue of, okay, if I look at 10 training data points versus 100 training data points, then what happens is the precision and recall is very, very, very different. Now, the other thing you have to look at, too, is it drastically, so suppose I change the 100 training data points that I'm putting in, if they're actually not well chosen, the EM algorithm that's used here, it actually doesn't converge. So if you don't have enough training data, Follagy-Sunter actually won't give you an answer. And hopefully, intuitively, this would also make sense because the method requires enough training data and actually, in order to actually have a stable solution. So if you don't have enough balanced matches and non-matches, it actually can't, the bottom measure is actually going to get a 0. And so it's actually, the EM actually won't converge there.
Just curious,
Yeah.
if you increase the number of training samples.
Yeah, so of course, if you increase the number of training data points, it's going to do really well, right? But then it's a really unfair comparison, right? Because we're not using any training data. So if we put training data into our method, it would do as well as Follagy and Sunter. So the whole point here is to do as fair as a comparison as possible to a semi-supervised method where we're using no supervision at all. Does that make sense?
Yeah, just
Yeah.
curious.
Yeah. So the same type of thing happens with deep learning methods. So like deep learning methods actually do much worse than this. So they basically tank when they have very little training data because they don't know what to do. So here, this is something so if you're looking at any type of semi-supervised method, you actually can't get something like this. So this is an example of typically what the Census Bureau or a human rights group or different types of social science partnerships that I work with, they want something like more than a point estimate. They want to know, well, what is the uncertainty? What is a credible interval? What is the actual error that you're getting out of the record linkage process? Because over here, because this is a categorical data set from Italy on survey, and the categorical information for a lot of the entities is the same, if I then put this into a linear regression, I really should, because the error is so large here, if I propagate this into the regression, that's going to have a huge impact as opposed to if I ignore it. So if I think about Follogi-Sunter and if I think about random forests or deep learning methods, they are ignoring this. Now, if I go over, so you can see it's quite different for all of the different data sets. So the more string values that we have, right, the less the error is. So here it's not going to matter as much, so it's going to matter a little bit, but not as much. And you can see here we also have a credible interval on the posterior regarding the uncertainty regarding, so if I didn't flatten this out and I looked at it, I'd have a full posterior distribution. I could look at the posterior mean, and this is the credible interval here. So this is just trying to convince you that depending on the data set, it really does matter regarding how much uncertainty is then going to get propagated into whatever prediction you're going to be looking at. And this could be quite important. So I'll come back to this in a minute. If I have time, this is just looking at the fact that we have a near linear speed up for different summary statistics that we looked at. But what I wanted to just quickly cover is, how does our approach handle data with little or no training data for a real application? So for this, I'm looking at an application to El Salvador. So they had a civil war from 1980 to 1991. And what the United Nations did is they created a truth commission called the UNTC to record the death casualties and disappearances after the conflict. And they did this about 10 years after the conflict. And so they actually did calls out by the newspaper, by radio, by television, and they asked witnesses to come in and record them. So they were recorded like this. And again, they were reported 10 years after. So then this was taken, and can anyone guess how it was then put into a computer, given the fact it was the 90s? OCR. So a lot of things like O's are 8s. So there's a lot of high level of noise. There's also a high level of noise because suppose someone died and then it's 10 years later and you're trying to remember the date of death, you're probably not going to get it quite right. So what we're trying to do here, right, there's data collected by multiple organizations, right? There's already been some normalization and schema alignment. What we're wanting to concentrate on is the actual entity resolution process. And then we're wanting to do a lot of analysis leading to, statistics, visualizations, multiple systems estimation, or understanding what is the actual size of the population, and doing some reporting that can be really useful to human rights groups. So in order to fully capture this, you actually can't use the model that I gave earlier. So the reason is it's not flexible enough. So it's not flexible enough for a lot of reasons. One is the fact that you have these very complicated Hispanic names, such as some of the ones that I have here. So you'll notice that a lot of them have, for example, 3 or 4 tokens. So with Hispanic names, what happens a lot is you'll have maybe 4 tokens of a name. So, for the first name, you have 2 first given names, and then your surname comes from your mother's family name and your father's family name. But then, because 4 names is very complicated to go around with, typically you'll drop 2 of the names. However, this isn't always consistent. So this is this is a bit difficult to model. So what we're looking at now is we still have the same basic type of likelihood function here. However, we're going to replace this with a non-parametric distribution here. So we're going to replace this with an HEA, where this is a Dirichlet process with parameter beta A, and this is the same psi that we looked at earlier, which crucially depends on the latent entity. Now, the latent entity is coming from G naught, and then if I think about what's going on next, so if I go back down to here, my distortion here is still a Bernoulli. Now, this is going to depend on theta, TA, and some zeta. So why am I changing this part here? Well, I'm changing this part here, and I'm going to change this to be a Bernoulli that now has a different factor, because what I want to do is I want to handle edge cases of names. So one example of an edge case, and I was talking to Betty about this when we were coming over, is Betty actually only has one name that she goes by. So we would call this an edge case in this type of problem. So if I think about the entire space of names I see, typically we see at least two types of names. So for example, you would see me as Rebecca Stortz and also Becca Stortz. But Betty actually only is Betty Chen. So if she's actually not going to be very comparable to any other person potentially in the data set. And this causes edge case problems when you're actually looking at this type of likelihood function. And this requires some perturbation of this hit and miss model, or else she's going to actually be misclassified quite easily. So this requires, again, some modification here. And so this is something that Neil has recently been working on, of building out this giant model. Now what he's working on, and something that we've written out recently, is basically breaking this down and collapsing it so that we can put it in basically a similar distributed type of system that we looked at that I showed before. So if I look at the same RL 10,000 data set, it works very, 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 very well on this model. So it actually works better than before. So you can see it's much, much, much more flexible. So the precision and recall are almost both at 1. So why is this the case? Well, if I think about Bayesian non-parametric models, they're incredibly flexible. So they're able to capture the distributions of different parameters, and I'm not having to tune things. So it's much, much, much more automated. Now, what am I having to give up? Well, the computation is going to be a bit more slower. Also, the relative error here is going to be 0.2%. And if I'm thinking about, this is now the uniform prior. So this has tuning issues and problems. So if I look at the Salvadorian data set, so this was a prior model that we looked at, so a kind of a special case of the model that I gave before, you'll see that this data set is hard to match. So if I look at the Pittman-Yor prior, the recall is incredibly low. And here, right, the precision and recall, while they're balanced, they're also really low. So why are they low? So why is this doing so well, but why is it having such a difficult time on this particular data set? So the reason for this is because we'll have names. We'll have something like this name. So we'll have something like these three names. So Carmen Alfaro, Jose Alfaro Gomez, and Carmen Alfaro Gomez. And this is where I think building training data is quite difficult. So we have training data for 2 municipalities. This was done by Mauricio Sedinle, who's actually at UW. And what my intuition is, and what I think is happening, is that if I had everyone in this room try and say who is co-referent here, we would get lots and lots and lots of different disagreements. And in fact, I think if we did this over a period of a week, we would get different disagreements within the same person. So the question is, are these the same 3 people? Are these 3 different people? how would you classify these records? So the model actually says these are two different people, and Mauricio believes that they are the same person. So if you asked me on different days, I would probably say on different days that it's plausible that they could be the same person. And on different days, I would say that they would be two different people that died in the same household in El Salvador. But I think it's very difficult in terms of training data like this. And so I think in terms of turning to methods like crowdsourcing or things like that, this really motivates why you should be using some type of unsupervised approach. And if you looked at many different types of precision and recall based on different types of crowdsourced data, you would get many different results. And so these are the types of things we're looking at now by looking at different types of evaluation metrics and how this would change.
So in that case, though, do you get a probability that highlights the fact that this is a questionable match?
So that's what we're working on. So Neil is working on a separate paper now regarding evaluations. So can you actually, if you take the actual definition of precision and recall, it's actually deterministic. But you can view that as you can actually view the definition from a population type perspective. And what he's looking at doing for a different paper right now is including basically uncertainty from the matcher. And so that's basically a different talk. And I'm happy to talk to you about it more offline if you have more questions. But the idea is you can include that, we believe, into basically a bias-corrected version of the precision and recall. But as you keep doing, as you would have different crowdsourced versions, you would get different versions of the estimated precision and recall. And if you think about how precision and recall is being computed, it's being computed deterministically. So the way we believe it should be computed is in a probabilistic fashion.
Yeah, I'm just thinking in terms of the output, not so much the algorithm to get you there. I mean, it seems like that particular example should be highlighted like an outlier or something that's just, you are not going to get a reliable answer here. And any attempt to do so is not really worthwhile. I mean, I would much rather just have that be, put into the unknown bin or something and just kept aside because the model is not going to be reliable. You just don't have enough information.
Well, the model isn't using it, right?
The output is going to be unreliable.
The output,
The output's going to be unreliable.
the evaluation will be unreliable. So I guess one of the questions they're having too is, that's a very good point. So should we just be marking? So there's actually lots of them that are outlying. So it's not a small fraction. There's actually a large fraction that we believe are like this case here.
Right, and that's just life in a world of incomplete data or fuzzy data, whatever you want to say. I mean,
Sure.
It depends on what's at stake here. If you're trying to get global statistical properties of a very large population like all of the U.S., that's one thing.
Yeah.
If you're trying to determine whether these 3 patients in a hospital are really the same patient because you're interested in treatments that were given to them in different places, well, this might be a life and death question.
Sure.
You don't want to, you
Yeah.
don't want to just be saying, well, I think. I mean, that's just not good enough.
Yeah, I agree.
So
That's why I
it's about
keep
how
saying
it's evaluated.
it's very application specific.
Right.
Yeah.
Exactly. And I would just want to know there's a way of applying the technique for the second kind of scenario where I'd much rather just be told where all the ambiguous cases are and not
Sure.
try to give me an answer that I can't trust.
So the other thing, I didn't mention this, but in terms of the output you can get from the model, you actually get a full set of who's who, and you get a posterior probability that they match. So in this life-threatening case of you're trying to maybe do some sort of prediction on health data or something for a very specific person, you can actually do something like looking up the probability that these 3 records are the same people and look at actually a posterior probability. And then you could actually, if you know, given that, you could actually label that as a yes, no, or a maybe, and then you could, based on that, put that into the downstream task. So that's another kind of, that's coming from the output. But, yeah.
Well, first let's thank Rebecca for the talk, and then we can take questions after that.